Hello, Chem 112 students. It's Virginia here, and I thought we could do a little bit more thermodynamic practice that goes beyond that worksheet. So let's go ahead and look at the graphs that are oftentimes associated with thermodynamics. And so here I have two sister plots. And so on these plots we have reaction progress on our x-axis and then free energy on our y-axis. We're keeping track of how that free energy changes as we go from 100% reactants, 0 products, all the way to 100% products and 0 reactants. Okay, so the 2 points that are marked here, so we have the delta G of formation of the reactants and the delta G of formation of the products. So you can remember that we get the delta G of our reaction by doing products minus reactants. And so we can look at that here. If we draw a line between these points, this value is going to be our delta G standard of reaction. Okay, and that's just the difference between products and reactants. And so we can draw the same thing here on the other plot, where we can see the delta G of reaction, the standard energy change. Okay, so if we look at the plot on the left, we can see that we're going from a lower energy reactants up to higher energy products. And so this is going to be a positive delta G of reaction. Whereas in the plot on the right, we're starting with higher energy reactants and going down to lower energy products. So here we'll have a negative delta G of reaction. Okay, so we would call this left graph endergonic, because we have to put in energy, it has to enter. And the plot on the right would be exergonic. Okay, and so there's one more point I want to mark on these plots, and that is what's going on at the valleys. Okay, so these valleys mark the lowest energy points, and that's where the reaction is happy. It's at its lowest energy. So these are our happy valleys, and at happy valley, we're at equilibrium. And to figure out the magnitude of KEQ, we're going to look at where that equilibrium point sits on the x-axis. Okay, so on the left plot, we can see that our equilibrium is sitting more on the reactant side. So if you remember at point 0, that's where we're going to have only reactants. And at point 1, we're only going to have products. And so since we're falling more to the left, our equilibrium is reactants favored, and we'd say that our KEQ then is going to be less than 1. And so if KEQ is less than 1, that means we're going to have a positive delta G standard. Okay, and then we can look at the case for our exergonic reaction, and we see that our equilibrium position sits more on the product side because it's closer to 1, which is when we only have products. And if our equilibrium favors the product side, that means our KEQ is going to be greater than 1, and that will happen when we have a negative delta G standard. So this kind of makes sense. If we're products favored, our reaction is going to be spontaneously going toward products, so we'll have a negative delta G standard. Okay, so KEQ and delta G standard are always going to be tethered together. They're linked. And we can remember that the equation that links these two together is going to be our delta G standard is equal to negative RT ln KEQ. And that is on the data sheet. So these graphs have more information than just telling us about where the equilibrium sits in the magnitude of KEQ. They can also serve as a roadmap for helping us think about what the non-standard delta G for a reaction is going to be. And so here I have my free energy plot, and I've marked where equilibrium is down in that valley. And we know that this is going to have a positive delta G standard, because we can see the products are at a higher energy than the reactants. And also that's reflected in the fact that our KEQ is telling us that it's reactants favored. Okay, but let's say we're at this point here on the plot. So we have more products. We're on the product side. And so that means our Q is going to be greater than our KEQ. We have more products. So anything to the right of our equilibrium point will be Q greater than KEQ. We can think, if we're trying to go forward from this position, we're going to have to put in energy, right, to move it up in energy level. You know, if this were a ball on a hill, we would have to put in energy to push it up. And so when Q is greater than KEQ, going in the forward direction is going to be non-spontaneous. And so we'll have a positive delta G for the reaction. Okay. And so what if we're working at concentrations then where Q is less than KEQ? So when Q is less than KEQ, we have extra reactants, so we need to make more products. And so at this point, if the reaction is to go in the forward direction, it's going to be moving downhill. And so our delta G of reaction under these conditions is going to be negative. Okay. So moving toward equilibrium is always going to be spontaneous. It's always going to be a negative delta G of reaction. And the equation we use to describe this is one that involves delta G standard, because that tells us where our equilibrium is, and an equation that involves Q, because that tells us where we are compared to where equilibrium is. And so to figure out what our delta G for the reaction is, we'll start with our delta G standard term as our reference point, and then we'll add a term that tells us where we're sitting in relation to equilibrium. Okay, so these graphs can be a roadmap to help us think about how changing concentration and where we are in regards to equilibrium will affect the spontaneity of a reaction at a certain conditions with regard to concentration. So now let's think about how this could apply with LeChatlier's principle. So I've written this reaction for the Haber process here. And we can think about how if we change something in the reaction, what's going to happen to the delta G associated. So let's say we go ahead and we increase the partial pressure of our N2 gas. So we add in more nitrogen, more N2. We know from LeChatlier's principle that if we add in more of our reactants, we're going to shift our equation to the right. We're going to shift to the right. And so that to the right is in the forward direction. So our delta G of the reaction will become negative. Because we're spontaneously going forward when we do that. And if we instead decreased the partial pressure of hydrogen, we'd be removing a reactant, and so the reaction would shift backwards to make up for that loss. And so now it's non-spontaneous in the forward direction. It's trying to go backwards, so this delta G reaction would become positive. And then if we say increased the partial pressure of the ammonia gas, now we've increased our amount of reactants, products, so we're going to shift back to make more reactants. And if we're going backwards again, our delta G reaction is going to become more positive. Okay, so we can relate this thermodynamic information back to our equilibrium discussion with LeChatlier's principle. Okay, and so that's all the extra stuff that I had that I wanted to include. So keep up the hard work and you all can make your way through this, okay? Great work. Keep it up.